Good evening, ladies and gentlemen. I'm sorry for the delay. We've had such a gratifying response to this lecture that we have a large number of people downstairs in the Lucas Lecture Theater, and we've had to ensure that they're wired up before we could start. It's my great pleasure as principal of King's to welcome you all to this very special event to celebrate the work of two very distinguished physicists, James Clerk Maxwell and Peter Higgs. I'm particularly proud that these great scientists have strong associations with King's. And these associations are particularly important to us because physics in particular, and the natural and mathematical sciences in general, are very important to King's and have been since the college opened its doors in the 1830s. As many of you will know, Clerk Maxwell is widely regarded as the most important physicist in the history of science, save for Newton and Einstein. And many of his great discoveries were made during the period between 1860 and 1865, when he was a professor at King's. Tonight's event is part of a program of 150th anniversary events to celebrate the great man, a program which began last year with a number of talks about the first color photograph which he took and which he displayed at the Royal Institution in 1861. In 1947, 100 years after James Clerk Maxwell started his undergraduate degree, Peter Higgs arrived at King's to read natural sciences in the field of physics. After graduating with a first-class Bachelor of Science degree in 1950, Peter took an MSc and studied for his doctorate in molecular physics here. He was awarded his PhD in 1954 for a thesis entitled "Some Problems in the Theory of Molecular Vibration." This work signaled the start of his lifelong interest in the application of the ideas of symmetry to physical systems. We're immensely proud that Peter Higgs holds 4 degrees from King's. 4 because, happily for us, Professor Higgs accepted an honorary doctorate from King's in 2009. In 1954, Peter Higgs took up a post at the University of Edinburgh and subsequently held fellowships at University College London and at Imperial College before returning to Edinburgh in 1960, subsequently becoming Professor of Theoretical Physics there. I'm delighted that Professor Higgs is with us tonight, and that furthermore, he has agreed that an annual lecture at the college will be named after him. Peter Higgs is one of the very few living scientists in the world who can claim to be a household name. This is due to his prediction of the existence of the scalar particle that is crucial for our understanding of 3 of the 4 forces of nature. In this way, he has made a fundamental contribution to physics with major consequences for our understanding of the origins of the universe. Known as the Higgs boson, this proposition is the primary object of inquiry for CERN's Large Hadron Collider in Geneva. This brings me to another scientist of great distinction, of whom the college is also immensely proud, Professor John Ellis. He has worked at CERN since 1978, where he was a pioneer in the Large Hadron Collider project and was the first theorist to propose a method for searching for the Higgs particle. Professor Ellis is the college's Clerk Maxwell Professor of Theoretical Physics, and he was named one of the top 25 most notable Britons by the Daily Telegraph in 2011. He'll be speaking in a few minutes. But first I want to hand over to our chairman for this evening, Ian Sample, the award-winning Guardian science correspondent, whose book Massive, about the complex concepts of particle physics, was shortlisted for the prestigious Royal Society Winton Book Prize last year. Please join me in welcoming him.
Thank you, Rick. Thank you, everyone, for coming along this evening. First, I'm just going to apologise if I cough and splutter. I've got this bug that's going around, and it nearly made me pass out on the way here. But I think we'll be okay. I'm hoping the adrenaline will crush it. Can I just get a show of hands? Who here considers themselves to have had scientific training? Okay. Who's been in the Maxwell Society at any point? All right. Okay. It's just nice to know who you're speaking to. Sorry, what have I done?
No.
Okay. You're putting your hand up. You're putting your hand up.
It's admitting to the Maxwell.
We'll come to that. I thought you were trying to catch my attention. Well, let's move on. I think with the Large Hadron Collider at CERN switching back on this week, and a final answer for the Higgs boson's existence or not, perhaps only months away, there could hardly be a better time for the lecture that we're about to hear. And we couldn't hope for a more qualified speaker than John Ellis. But before John takes us through the physics of Maxwell to Higgs, we'll hear from Peter Higgs himself. Now, you all know, I'm sure, that James Clerk Maxwell was here at King's 150 years ago, and he showed that the electric and magnetic forces, which were previously thought to be separate phenomena, were actually intimately related and two sides of one unified electromagnetic force. Nearly 50 years ago, Peter Higgs, who spent his student years here, was one of several physicists to publish a theory that paved the way to another important unification of nature's forces. Though far from clear when the theory was written down in '64, the Higgs mechanism, as it came to be known, later helped unify the electromagnetic force with the weak force, which earned other people a Nobel Prize. Now, a while ago, I wrote a book about all of this, and while researching that story, I came to King's to go through the archives of the Maxwell Society, which met after lectures and often had prominent physicists come along as invited speakers. Peter was an active member of the society. Now, last night I dug out my notes, which I took from several burgundy books with yellowing pages from the archives, and they spanned the years 1947 to 1950. And they're full of some wonderful details. Arthur C. Clarke, another alumnus of this college, came here to talk about interplanetary travel. Sir Edward Appleton gave a lecture on the prospect of radio waves from alien civilizations. And Lawrence Bragg spoke about crystallography. It's probably one of the more hard-going talks. But among the hard physics are other hints of life here at King's, and especially the Maxwell Society. In 1950, the Maxwell Society laid plans for a Christmas party. And as one of the members of the society noted, who I won't name, such a function would have maximum success if the ratio of the sexes was 1:1. And to achieve this purpose, it was decided to invite the exclusively female Bedford College. Now, you might not remember, Peter, but according to those minutes, on this day, March the 14th in 1949, you were elected president of the Maxwell Society. And the first invited talk under your presidency, according to the notes I got, and I'm a journalist, I may have got it all wrong, was a talk by Charles Coulson, whose talk was called Any More Physics? ? And it was about how physics discoveries were gathering pace. And he ended his talk by saying that in 10 to 20 years' time, all physics, I quote, would be known, unless something entirely new turned up, such as, and I quote again, telepathy in the brain. I mention this only so you know not to trust everything these guys tell you, especially when it comes to predicting the future. Now, Peter was extremely patient and kind to me when I wrote that book, and it's a real pleasure to introduce him here tonight. So please welcome Peter Higgs.
Well, thank you, Ian, for introducing me. I've been asked to say a few things about the early history of how I came to acquire a certain notoriety in particle physics. If somebody had told me when I was here as a student that I would be standing here today with my name as part of a lecture whose title involves the name Maxwell as well, I would have been, I would have not believed it. I'm greatly honoured by this connection. Ian mentioned the Maxwell Society, and perhaps I might mention in passing that this is, I think, only the third occasion in which I've got up at King's College and talked about anything in public. The first was my presidential address to the Maxwell Society at the time that Ian mentioned, but in spite of that first occasion, I was invited back in 1983. This was at the time that the intermediate bosons of the weak interaction electroweak theory had just been discovered, the W and the Z. So when asked to give a talk, I provided the rather cheeky title, Putting Maxwell in His Place. And the talk was devoted to telling how Maxwell's theory had essentially been enlarged to provide a framework for the weak interactions as well. Now, my part in this story, which occurred in 1964, is, I think, not quite as it appears on the back of this card, because to me is attributed the theory of mass, but I didn't do that. The great innovator in 1960 was the Japanese-born American theorist Yoichiro Nambu, who formulated a theory based on an analogy with superconductors. And what he did in one way, and Geoffrey Goldstone of Cambridge at about the same time did another way, was to show how the idea of spontaneous symmetry breaking in particle physics could explain masses of Fermi particles like electrons and, as we now know, quarks, though that Nambu didn't know about quarks in 1960. What I did a few years later, and several other people about the same time, I was not the first to publish, I was the second to publish, the first two being Robert Brout and Francois Englert of Brussels, was to fill in a gap in the Nambu Goldstone program. The way they had left it to seem to be a problem because the theory seemed to predict massless particles of zero spin, which were got to be called Goldstone bosons. And I happened to spot the way to evade that, as did some other people. And it happened rather by chance when I realized in July of 64 that the problem with what had become known as the Goldstone theorem was that its axioms were too strict, the axioms needed for the proof of the theorem, and the obvious theory which didn't obey those axioms, which was perfectly good relativistic quantum field theory, was quantum electrodynamics, the quantum version of the Maxwell theory. And this was a realization which just put together two things I knew already but hadn't connected over a weekend in the middle of July. So the way it then happened was that I wrote a short paper which said there's a way out of the Goldstone theorem. You have to use a Maxwell type of theory to do this. And that was accepted for publication in the journal Physics Letters. And then having written the paper saying there's a loophole in this theorem, I did the obvious thing. I put together the two pieces in a model theory, which has become known as the Higgs model, and that model theory could be characterized as Goldstone meets Maxwell, because the potential energy, the wine bottle shape or Mexican hat shape, was already in Goldstone's work in 1960. It's not an invention of mine. And to my amazement, the journal rejected that paper. This was the one which had the physics in it, but they didn't think that it had very much to do with particle physics for some reason. So I rewrote it with some additional material and sent it across the Atlantic to Physical Review Letters, where it was accepted. And I later discovered it was accepted perhaps because the referee was Yoichiro Nambu, who'd started all this. In the course of rewriting the paper, I added some material because I thought maybe I haven't made the connection with physics clear enough. And it was in this rewriting that I mentioned these massive spin zero particles, which there would be in theories of this type, which now are known as Higgs bosons. Fast forward to many years later, it took quite a few years before this type of theory was actually applied to the right system. For many years, people like myself and Engler and Brout tried to apply it to strong interactions in particle physics, and it was Stephen Weinberg and Abdus Salam who found the right thing to do with it. And it was a few more years yet before the theory was shown to be viable by the work of Veltman and Hooft, and a few years before it became something which could be sold to experimentalists. And the man who was perhaps most responsible for telling experimentalists that they should look out for this so-called Higgs boson, which was a consequence of this kind of theory, which now seemed to be working in other respects, was John Ellis. So it's a great pleasure for me now to hand over to John to give his lecture. Thank you.
Well, there used to be a saying in the music hall that you should never appear after children or an animal act. And I feel somewhat the same way being asked to talk after Peter Higgs. So, as you will have gathered, Peter is an extremely modest man, and I think actually he's deeply embarrassed by all this fuss that's been made about this, little boson thingy. But I think that everybody knows that Maxwell is important. In fact, here's a quotation by Albert Einstein saying that the work of James Clerk Maxwell changed the world forever. We'll see whether people in future years come up with similar quotations about Peter Higgs. So, King's at the moment is talking to the world about its questions, and King's is promising to provide answers. When I talk about particle physics, in particular when I talk about Maxwell and Higgs, I like to take as a sort of opening text this famous painting by Gauguin, where people are asking some very, very basic questions. So they're asking them in French, I translate them into English. Where do we come from? What are we? Where are we going? So I think we all agree these are important questions. And I would argue that answering these questions is precisely the objective of fundamental physics. It's precisely the objective of people like Clerk Maxwell, like Peter Higgs. And simply stated, our objective is to try to understand what the universe is made of, what are we, how the universe got to be the way it is, where do we come from, and perhaps some insights into what may happen in the universe in the future, namely, where are we going? So, James Clerk Maxwell is one of the forerunners of this effort. Peter Higgs is one of the most important successors in this effort. And what I'm going to try to do is to describe how their work is connected together and what is currently occurring in this attempt to understand what the universe is made of. So this is another image which I rather like of the quest for the trail for unification. where gradually as you go into the distance these tracks converge, and maybe there's a little hint of something on the horizon, which perhaps might be the infamous Higgs boson. So I will describe how this trail towards a unified theory of everything goes from Maxwell's theory of electricity and magnetism through to the ongoing search for the Higgs boson at the LHC. So let's cast our minds back a couple of centuries, the first part of the 19th century. So people have known about electricity ever since the ancient Greeks. In fact, the word electricity comes from the Greek word for amber. Of course, we know that one of the ways of generating electric sparks is by rubbing amber. But it was pretty much of a curiosity, I would say, until the first half of the 19th century. Another curiosity, of course, was magnetism. Magnetism, actually that's again goes back to the ancient Greeks. It's named for the part of Greece where magnetic lodestones were found. Now, magnetism actually did find a use before the 19th century. In fact, it was used for navigation, as far as I can make out, almost at the same time, both in China and in Europe, started to be used for navigation. But I think at the beginning of the 19th century, nobody could have seen the connection between electricity and magnetism. And nobody, I think, foresaw the importance of these rather abstruse phenomena, the fact that they would completely revolutionize the way that people live 200 years later. So one of the key figures in this, even before Maxwell, was, of course, Michael Faraday, who did much of his most famous work at the Royal Institution over on the other side of town. He actually established the principles on which electric motors work and did much of the fundamental experimental work which provided the basis for James Clerk Maxwell's theoretical speculations. And I have read that Einstein's study when he was working at Princeton in the 1930s had on the wall pictures of Newton, Faraday, and Maxwell. So that's the level at which we're talking. So as you already heard, James Clerk Maxwell was professor at King's for 5 years between 1860 and 1865. He did a lot of remarkable things while he was here. As the principal was already mentioned, actually it was in 1861 that he took the first colour photograph, and it was shown at the Royal Institution. Needless to say, it was of a Scottish tartan. Of course, his most famous work is the one which we're here to think about this evening, namely the work in which he unified electricity and magnetism, basically giving us the word electromagnetism. So there are various aspects to this work which are of fundamental importance. For example, he predicted the existence of electromagnetic waves. Now, those of you who are not physicists might wonder, well, why should I care about electromagnetic waves? Well, actually, of course, that is what light is, that's what radio is. So every day you use Maxwell's discovery in a myriad of different ways. In fact, when he made this original prediction that there should be these waves, he was also able to calculate the velocity of these waves, and he calculated something which was very similar to the velocity of light. And I can just imagine James Clerk Maxwell, doing his little calculation, getting the velocity of light, getting the right answer, and jumping out of his bath or his lock or whatever, and running around shouting "Eureka!" Anyway, he did a whole bunch of other things as well, which I don't have time to discuss in this talk. But I think this already indicates to you why it is that Albert Einstein was such a fan of James Clerk Maxwell. Here's another one of his quotations. So the thing that physicists chiefly think of when they think of Maxwell is Maxwell's equations. So it's often said that every time you put an equation in a book, you lose half the readers. So this is the point where I lose half the audience. So here are Maxwell's equations, which unify electricity and magnetism. Those of you who are not physicists are going to have to take it from me. E stands for electricity, B stands for magnetism, and you see that they kind of fit together in some way. Now, quite apart from what I already mentioned, this unification of electricity and magnetism, and the fact that Maxwell was able to calculate the velocity of light, these actually provided the prototype, the basis for Einstein's special theory of relativity, and hence, of course, eventually Einstein's general theory of relativity. So, as you know, there's been a little bit of a bother recently about whether neutrinos really travel at the speed of light or not, whether it's a true universal speed limit, as Einstein proposed based on Maxwell's work. The latest word from the shop floor is it seems that maybe Maxwell and Einstein are okay, but we'll come back to that later maybe. Now, of course, when people like Faraday and Maxwell were doing their work, they were interested in understanding fundamental physics problems. They could not foresee what the applications, what the implications of this would be. But there's this wonderful quotation from when Maxwell met Gladstone. And I think that all of us fundamental scientists should repeat this ad nauseam whenever we meet college principals or politicians. Okay, so I talked about electromagnetic waves. So they were proposed by Maxwell. In fact, they were observed some years later by Heinrich Hertz, whom you can see here. It seemed to be a fashion at the time for physicists to wear beards. Well, of course, both Maxwell and Hertz have got a lot to answer for. And as I said, this is just one example of how one never knows where fundamental physics may lead. Now, the next step in this unification trail that I would like to mention is our old friend Albert. And it was he who suggested that light, the electromagnetic waves, electromagnetic radiation that had been postulated by Maxwell, that this might actually come in little lumps that we call quanta. So this hypothesis was introduced previous to Einstein's work, but he was the person who actually brought out the physical reality of this, and this actually enabled him to understand what happens when light hits matter, in particular when you shine light on a piece of metal, the way in which electron particles come out. So this may again seem somewhat abstruse, but of course the photoelectric effect is the basis for many aspects of science. It's interesting to note that although to the general public Einstein is best known for his theories of relativity, in point of fact, he got the Nobel Prize for the photoelectric effect. So this again indicates the importance that physicists attach to the work of Einstein in this field. So he took, as I said, the idea of electromagnetic waves and radiation postulated by Maxwell and applied the quantum idea to it. Okay, so now let me talk a little bit about the structure of matter and connect back to the work of Einstein that I just described. So it's been conjectured ever since the days of the ancient Greeks, and this is now established by modern physical theory, that all matter is made of the same limited number of fundamental constituents. So we know about atoms, everybody's heard of atoms. It was discovered by Rutherford almost exactly 100 years ago that atoms contain electrons going around a relatively small atomic nucleus. In the first half of the 20th century, it was discovered that these nuclei are made up out of particles called protons and neutrons. And in the second half of the 20th century, it was established that inside these protons and neutrons are quarks, which Peter already mentioned in his opening remarks. So the business of us particle physicists is to understand these fundamental objects, these electrons, these quarks, the photon that I mentioned on the previous slide, and to understand the forces that act on these various different types of particle. So I've talked about electromagnetism. I think perhaps now is the time to talk about another force, namely the strong nuclear force. So the strong nuclear force is the one that holds nuclei together, holds protons and neutrons together inside nuclei, and at a more fundamental level, it holds the quarks together inside the protons and neutrons. So we have a theory for how this works, a theory which works extremely well, by the way, and it's basically modeled after the theory of James Clerk Maxwell. And according to this theory, analogous to the photons of Einstein, you have particles called gluons, whose job it is to glue together those quarks inside the nuclei. And these particles were indeed discovered back in 1979 using a method that we'd suggested a few years previously. And so these gluons, or this gluon, is the second type of force particle to have been discovered. Now, Peter, in his opening remarks, already referred to the weak interactions and the particles that carry the weak interactions, which were discovered in 1983. So, again, the weak interactions, these are responsible for radioactivity. Again, the theory there is modeled after Maxwell. But in this case, there's a difference. Whereas the photon is a particle without mass that always travels at the speed of light, the carrier particle of the weak interactions, the W, was predicted to weigh something like 80 times as much as a proton, as much as a medium-sized nucleus. And so it required quite a lot of experimental effort to make this thing, and it was indeed discovered in 1983 in a big experiment at CERN led by Carla Rubio, whom you see here, who is smiling, perhaps understandably. So putting together electromagnetism, the weak theory, and the strong interactions, as I've described, we have the standard model of particle physics. So as Peter has already mentioned briefly, this was put together in the 1960s by Abdus Salam, whom you see here. You can see immediately he doesn't come from King's. In fact, he comes from Imperial College, but originally from Pakistan. But we'll forgive him the fact that he comes from Pakistan. Glashow and Weinberg, two American physicists, and they put together the ideas that had been developed by Peter Higgs and his colleagues and made a consistent theory of the weak and electromagnetic interactions. So this was verified in a whole series of experiments. This, for example, is one of the key experiments done at CERN in 1973, back in the days when physicists still wore lab coats. And very detailed experiments were done at CERN in the 1990s, which confirmed the theory with high precision. So what does this standard model consist of? So what are we made of? What are the particles? What are the fundamental particles of matter? So here we have on the top right the electron, misspelt. Below that you've got two other analogous particles. We don't know why there are two other particles, but there are, the muon and the tau. Over on the left-hand side, we've got the quarks. There are 6 of them. We don't know why there's 6. That's just the way things are. And in between, we have the neutrinos, the mysterious particles that have been causing a whole lot of excitement over the last few months that unfortunately may now be dying down. Okay, so those are the fundamental constituents of matter, and these are the fundamental interactions. So we've got the electromagnetic force, so that's James Clerk Maxwell. We've got the strong nuclear force, acts in pretty much the same way, but with a gluon instead of a photon. We've got the weak nuclear force, which looks rather similar, but with a big difference. That big difference is the W there. That W there, as I mentioned a moment ago, is a very heavy particle, weighing as much as a nucleus. So the big dilemma in constructing the standard model was to understand how it could be that you could have some particles, like the photon, the gluon, that have no mass, and the W particle, which is as heavy as a nucleus. So what you see described on this slide, I characterize as the cosmic DNA. These particles, their properties, somehow encode all the information you need to make all the visible stuff in the universe. Now, astronomers, cosmologists tell us it's a whole bunch more invisible stuff, but maybe that's for the next lecture. Okay, so we got this standard model. It works incredibly well, but we have this problem of why some particles have mass and some do not. So those of you who did a bit of physics at school may remember that weight is proportional to mass. Newton told us that. And everybody knows that E is equal to mc squared, right? So Einstein related energy to mass. Unfortunately, neither of these honourable gentlemen remembered to tell us where the mass comes from in the first place. And that is where this gentleman comes in, looking at perhaps a shade younger than this evening, certainly with different glasses. Okay. And the key thing about his theory is that there is a way of testing it experimentally, and that is to look for this infamous Higgs boson that we've all been yattering on about. Now, I should perhaps try to emphasize yet again that this Higgs idea is a big deal. Suppose that particles did not have masses. What would the universe look like? It wouldn't look like anything that we would recognize. There wouldn't be any atoms, for example, because if electrons had no mass, then they would just run away from nuclei at the speed of light. In fact, it's even questionable whether there'd be any nuclei at all, because the weak forces responsible for radioactivity, which are fortunately relatively weak, that's why we don't glow at night, okay? But they are weak because that W particle is heavy. Life would be completely impossible if that W particle was massless, like the photon. So I think we've got a lot to be grateful to Peter Higgs and his friends for having saved us from. So how does the Higgs trick work? Well, it's getting a little bit warm in here. So I showed you Maxwell's equations. Which are frequently shown on the t-shirt. So you can also put the standard model on the t-shirt. And Maxwell's equations are summarized on the top line. The second line describes the way in which electromagnetism acts on particles like electrons. So we can say this is Maxwell, this is Einstein. Those two lines have been amply confirmed by experiment. The two bottom lines, that's where Higgs comes in, and there is absolutely no direct experimental confirmation of those two lines. And that is what we're trying to do now in experiments at CERN. So, that's the theory, but there won't be an exam at the end. But I would like to propose to you an analogy which may be helpful in thinking about this. So the idea is the following. you should think of space as containing stuff. There's a medium throughout all of space, what in physics we call a field. Well, in fact, you've heard of electromagnetic fields, you've heard of gravitational fields, so those are all sort of localized around electric charges and the sun and things like that. But imagine a field which is absolutely uniform, continuous, homogeneous throughout all space. Think snow in Siberia. Okay? So you've got this immense Higgs snow field extending as far as the eye can see and further. Now try and cross it. Now, if you're lucky, you may have skis. Then you skim across the top of the snow. You don't really interact with the snow. You travel very fast. That's like a particle traveling at the speed of light. A photon, maybe. Now suppose you've got snowshoes. You've got snowshoes, then you sink into the Higgs snow field. You travel at a slower speed than the skier. That's like a particle with mass that travels at less than the speed of light, because of your interactions with that universal Higgs snow field. And then finally, maybe you're crazy enough to try to cross Siberia in your boots. You're going to go very slowly because you're going to interact very strongly with that Higgs snow field. It's like a particle with a very big mass that always travels much less than the speed of light. Okay, so that's the basic idea for how some particles travel slowly and have mass. Some particles travel fast, the speed of light, and have no mass. Next step. Just as Einstein postulated that there was a quantum of the electromagnetic field, is there a quantum of the Higgs field? Well, of course, snow is quantized, right? Snow comes in lumps called snowflakes, right? So you can think of the Higgs boson as being effectively the Higgs snowflake. Now, this analogy can be carried a little bit further. One should always be careful not to take analogies too far, but snowflakes, of course, are known all to be different from each other. There's an infinite number of snowflakes. So actually you can get a big fight amongst theoretical physicists as to whether the Higgs boson is a single elementary particle or whether it's actually just one of an infinite family of composite things made up out of other little bits. And hopefully the LHC will soon tell us the answer. So when I think about the situation in particle physics, I often think of it as like being in a room with no windows. We think there is stuff beyond the standard model, but we can't see it. But there is a door, and I firmly believe that when we open that Higgs door, then it will provide us with some clues as to what is lying beyond the standard model. Let me just mention one example. Cosmologists, astrophysicists tell us that there's between 5 and 10 times as much invisible dark matter in the universe as the visible stuff. There are various theories according to which that might be fabricated at the LHC in the collisions, and many of those theories link it to the existence of the infamous boson. Now, that's not the only thing which experiments at the Large Hadron Collider are looking for. No, they're not looking for the Starship Enterprise. But they are looking at antimatter physics. In fact, it sometimes seems that CERN gets as much publicity from looking for antimatter as looking for the Higgs boson. Whether this has anything to do with Tom Hanks, I don't know. I should reassure you, of course, that physicists can't make enough antimatter either to power up the Starship Enterprise or to destroy the Vatican. But there is a very important issue here, which is where does the matter come from? I talked earlier on about Bill Gann's questions. I raised the question, where do we come from? Where does the matter in the universe originate? So this actually became an issue back in the 1920s when Paul Dirac, whom you see on the left and the anti-Dirac on the right, he realized that all the known types of particle should be partnered by other types of particle with equal and opposite properties, the same mass but opposite electric charge. This is another example of how something which is apparently extremely abstract, because he was trying to put together quantum physics and relativity, something very, very abstract and fundamental, actually has applications. Now thousands of people have medical diagnosis every year using antimatter particles. Anyway, what we want to understand is why it is that matter and antimatter turn out to be not quite equal and opposite, and this may be linked to the fact that the universe, as we can see looking around us, contains matter but no discernible amounts of antimatter. This is my friend Albert again, somewhat younger in this picture, and I actually sort of fancy that he looks rather sad, maybe because he somehow anticipated that he was not going to succeed in constructing a unified theory of all the interactions. He was very much inspired, as we discussed earlier, by the work of Maxwell. I think one of the reasons why he did not succeed was because he didn't have the ideas of Higgs. That's another story. Anyway, many of the ideas that Einstein did play with, again, are now being explored at the Large Hadron Collider. So, here is the Large Hadron Collider. So, you may not know what a hadron is, but you know what large is. So there it is, 27 kilometers in circumference. Collider, particles go around it and hit each other. And hadrons, well, that's our jargon name for the protons and nuclei that we send around in those collisions. This is probably the biggest scientific laboratory in the world, and I hope by now I've convinced you, that there are good reasons why it has to be so big. So here is what you would see inside the tunnel. So we have to imagine that you're something like 100 meters underground. As I said, 27 kilometers in circumference. You can just make out the curvature of the accelerator over there. And inside the magnets that you see when it's operating, there are hundreds of thousands of billions of protons going around in opposite directions. Each of them has approximately the energy of a fly. It travels at 99.9999991% of the speed of light, which means that it goes around the ring 11,000 times per second. And fortunately, unlike the UK, Switzerland is part of Schengen, so the protons don't have to show their passports every time they go in. So, trying to understand where mass comes from, trying to understand the dark matter in the universe, trying to understand the stuff that filled the universe when it was a fraction of a second old, and maybe trying to understand how we got to be here, where the matter in the universe comes from. So this is quite a big technological enterprise. I'm a theoretical physicist like Peter Higgs, like James Clerk Maxwell. So I claim no credit whatsoever for the technological superlatives that are involved in making this thing work. So here's a picture of connection between two of the magnets. Inside you've got the tubes where the protons go around. The vacuum inside those tubes is much better than in interplanetary space. It has to be, because you want the protons as they go around to hit each other and not to hit gas which is sitting in the tube. Those magnets have to be very powerful in order to get very energetic protons going around in circles. To make those magnets very powerful, you cool them down to very close to absolute zero. In fact, the temperature inside those magnets is less than 2 degrees above absolute zero, whereas the temperature of outer space, the radiation in outer space, is 2.7 degrees above absolute zero. So I would claim that particle physics is 0.8 degrees cooler than cosmology. Except when we make collisions. So when you make collisions, for a very brief instant, you create in an incredibly tiny volume effectively temperatures which are perhaps 1 billion times higher than in the heart of the sun. And those collisions produce sprays of particles that come out, and the job of the experimentalists is to see what those particles are. So there are 4 big experiments looking at those collisions. King's is involved in the one at the top right, the Atlas experiment, in the person of Bobby Acharya, who recently joined our faculty here. Some of the others of us are involved in a very small experiment which is planned to look for magnetic monopoles, but that's still in the future. Just to give you some idea of what's involved in putting together these experiments, I'll just show you an image of the assembly of the Atlas experiment in its underground cavern. The cavern, you have to remember, is about 80 or 100 meters underground. It's as big inside as the nave of Notre Dame Cathedral. And to convince you that the resulting object is big, this is a person, real person, not a Lego person. So, whoops, something just happened. Okay, well, we can just watch Atlas being assembled again. That's okay. So, involved in this quote-unquote experiment are some 3,000 scientists and engineers, something like 1,000 PhD students from 38 countries, and somebody counted up all the pieces and calculated there are more components than in a Saturn V moon rocket. So you can understand perhaps why Peter Higgs is just a little bit embarrassed about the fact that an enormous amount of effort is being put into proving him wrong. So this is a computer simulation of what the infamous boson might look like in one of those big LHC detectors. So you have to imagine that 2 protons have collided diagonally like this. They produce perhaps 100 charged particles coming out, a whole bunch of other particles you can't see, neutral particles. And so then you have to use a very sophisticated computer system to figure out what the particles were that came along what tracks. And somewhere in all this mess, there is concealed a Higgs boson. Now, you can't see the Higgs boson because it's a neutral particle, doesn't leave a track, but it's a very unstable particle. It decays very quickly, sometimes into charged particles, and maybe those charged particles you can see. In fact, in this simulation, there's 2 energetic charged particles on the right-hand side. You can see those sort of blue towers coming out. And there's a couple of other energetic particles over there on the left. Now, it should be said that, okay, it's not so obvious how you pick out something like this, in particular because you have to trawl through perhaps trillions of events in order to find the right one that actually contains perhaps a Higgs boson. So, very happy to show you the first Higgs event at the LHC. So this is when Peter visited the Atlas experiment a couple of years ago, without glasses. Just to remind you, just in case you'd forgotten. Okay, but now I want to show you a real event from the Large Hadron Collider, seen in the Atlas experiment, that might, just might, be an example of a Higgs boson. So it's a bit bright, I'm not sure whether you can make it out. But you can perhaps see that there are 4 long, straight red lines coming up. So those red lines are energetic particles that might have been produced by the decays of a Higgs boson. Those are actually, if I'm not mistaken, 4 muon particles, which is the heavier partners of the electron. So Atlas has a few events that look like this. There's a rival experiment, which is associated with another college towards the west of London that we won't mention. And both of them have, interesting hints of what might possibly turn out to be a Higgs boson. So I wanted to bring you bang slap up to date. This is a compilation of the data that were shown at a specialized particle physics conference last week. Difficult to make out what's going on. So you can see at the top left there, 1. Okay. Now, there's a horizontal line going across. So if you can see something at that level 1, that might be a Higgs boson. Now what you see is there's a whole range from the left to the right where what is actually seen, the black line, is far below 1. So there's no Higgs boson, all the way from over on the left there to beyond the right-hand side. But you can see a little wiggle which pokes above 1, and that's what all the excitement is about. This might be the first hint of the existence of a Higgs boson. But I should say, by the way, that that previous picture and this picture that I'm showing you now are unofficial pictures. These are not done by the LHC experiments themselves. It's done by an independent blogger who used to be a theoretical physicist, and he does a pretty good job. But anyway, this is an unofficial combination of the data. And again, what you see here is that there is a large range of, this is the mass of the Higgs boson, large range of masses of the Higgs boson where there's no sign of anything. And then, maybe, just maybe, there's something that could perhaps turn out eventually to be a Higgs boson. But it's not yet established that this thing actually exists. If it does exist, we don't know exactly what it is. So, Peter, you're going to have to be patient for a little while longer, but maybe not that much longer. Soon maybe you will finally emerge from the background. Okay, so I wanted to just finish with a couple of little messages. So I think that in the first half of the talk, I made the argument that innovation is based on fundamental science. So Maxwell unified electricity and magnetism, and he gave us the mobile phone. Einstein formulated his theory of relativity, and you may or may not know that the GPS system, actually, you have to take into account the effects of Einstein's special and general relativity in order to compute your position at the timing using GPS. So these are just examples for how physics of 150 years ago or 100 years ago turns out to have everyday applications. A question that I often get asked is, will the Higgs boson turn out to be useful? I have absolutely no idea. But neither did these guys have any idea at all that their fundamental discoveries would be useful 150 or 100 years later. One thing which I can say is that the search for the Higgs boson is useful. So this is a picture of Tim Berners-Lee, who invented the World Wide Web while he was working at CERN, precisely in order to enable those thousands of physicists to collaborate together effectively and share their data. And neither he nor anybody else realized what impact this would have. I phrase this somewhat carefully because I have no idea how much tax they actually pay. I always read Private Eye, who is always telling me about these scams that mobile phone companies get up to in order to avoid paying tax. That seems to be a recurrent theme, tax. Okay, so it brings me to the end of my talk. I hope I've convinced you that the LHC, the Large Hadron Collider, may revolutionize physics. Maybe it'll discover the Higgs boson. Maybe not. I often actually think it would be more exciting if it proved there was no Higgs boson. And I certainly think that the discoveries that we make at the Large Hadron Collider may change our view of the universe. Just to finish, I wanted to tell you a little story. So, 30 years ago, Meryl Streep visited CERN. Well, that actually would have been more exciting. So, Mrs. Thatcher was introduced to a bunch of British physicists. What do you do, young man? Meryl Streep does the accent much better. So I said, well, I think of things for the experiments to look for, and then we theorists hope that they find something different. Wouldn't it be better, young man, if they found what you predicted? To which I replied, well, if they just found what we predicted, then we wouldn't really feel that we were going to learn anything. So in the same spirit, I hope that the Large Hadron Collider will become famous for discovering something a little bit different, at least, from what we predicted, although maybe not something totally different from what Peter Higgs predicted. Thank you.
The legend that is John Ellis. You must be itching with questions. I know I am, but it's your night. So we should have some people with microphones to run around. So get your hands up if you've been thinking of questions. I wasn't quite sure how we get questions from the overflow room. So if anyone has an idea how we do that, let me know somehow. Have we got any? I can't see any questions. Any questions yourself? Come on, you can't know all this stuff already. Okay, there's Chuck down here. Can we see? Where? Just down here.
Hi, I'm James Aratoon. I'm interested in your talk. It's very good. One thing I'm interested in is the latter stages of the LHC, which is when you increase the energy and you start seeing the heavier particles. Is there a relationship in the collisions, not just on mass, but perhaps in velocity, that you can predict perhaps, say for a dark matter particle, not only the mass element, but what the sort of dark matter temperature would be, such that you could put limits on how dark matter would interact with real matter. I don't know whether that makes sense as a question, but there's two aspects to energy, isn't there? There's the mass, visual mass, and there's the velocity or the kinetic component.
So let me try to come up with an answer to your question. So as the energy is increased, and it's planned to increase it slightly this year, but not by a big amount, but then in 2 years' time, it's hoped to increase it by almost a factor of 2. When you do that, then you with higher energy, you can produce heavier particles, or you can produce light particles, but at a larger rate, which I think is perhaps what you were thinking about. So for example, if you're interested in looking for the Higgs boson, you actually produce more Higgs bosons if you're operating at 14 TeV in the center of mass than if you're producing at 7 TeV in the center of mass. But I think from the point of view of dark matter, the interesting would be to produce the particles which are associated with the dark matter. And various studies have been done that have shown that if you're lucky with detailed measurements at the Large Hadron Collider, in particular at higher energy, then you could measure sufficiently many of the properties of these particles to figure out whether what you think is a dark matter particle actually does its job, when it has the right density, when it has the right interaction rate, and so on. So yes, high energy will be crucial for that.
Any more hands up? Got any more questions on this? Yeah, so lady right at the back, and for someone, be easier if you were this side probably.
Yep.
If you shoot along here, then you're 7 people over at the back. If there's anyone else who's got a question, we take a few at a time, and then we can. How many microphones? First one. Why don't we go to the lady at the back, 7 people in, and then we'll have some other people teed up, just to make sure everyone gets their questions in.
Yeah, maybe send a microphone into the middle of the aisle.
Oh, there we go. Hi. Of elements and found out that all the elements that have charge also have mass. I mean, all charged particles must be massive. But not all massive particles should have charge. So I was wondering if you have any relationship between mass and charge, or does charge come from mass somehow?
So it's an interesting question. Theoretical physicists have debated that a lot, whether it would in principle be possible to have a massless charged particle. I don't know of any reason why that could not happen, but as you say, it doesn't. All the charged particles do have masses. In fact, we know that they cannot be a massless charged particle. That would be seen eons ago, at university. Completely different if there had been a massless charged particle. But that's all my theoretical colleagues know better than I don't know of a reason why that would be the case, but it is.
This gentleman here in the light shirt, that's tried to share the question. Did you have a microphone? Okay, sorry, we'll come back to you.
Okay, got it. That's loud, sorry. In mid-December, the LHC announced the findings of the data from the 2 detectors, and the bump in the data was about 126 or 125 GeV. Gordon Kane claims that by early December, using a variation of string theory, he had calculated the Higgs particle mass to be somewhere between 122 and 129. And that was posted apparently in a preprint on arXiv before the Higgs results came out from CERN. So my question is, do you think the LHC has actually provided one of the first experimental confirmations of a prediction of string theory, and is it the Higgs particle?
Well, first of all, it's a question of whether it's the Higgs particle, and this we don't know. Okay? The Higgs particle has very special properties. It gives other particles their masses, so its connections with those other particles have to be proportional to their mass. That is not yet very well. Also, that's crucial, the Higgs boson has no intrinsic angular momentum. It's a sort of isotropic particle. And that hasn't been checked either. So we don't know whether what we have not yet discovered is a Higgs boson or not. Now, it is true that Gordon Kane and collaborators wrote a paper predicting 125 GeV. Other people also wrote papers predicting 125 GeV. Other people wrote papers predicting some other mass. So those other ones may be wrong, right? But there's certainly other people who I think have as much claim as his collaborators to have made a successful prediction. Now, some of them are inspired by string theory, some of them are not inspired by string theory. The ones that are inspired by string theory are actually inspired by different interpretations of string theory. So I think it would be too early to make a strong claim.
Who else had questions? I've lost track of where the hands were. You have the microphone already. Who else is... Just make sure... Is anyone at the top got questions? You just missed the whole lecture because you've got a funny seating up there. Okay, we'll go to this guy first and then we'll come to you, okay?
Professor Ellis, thank you for your analogy of the snow field, which I'll use this evening to explain the Higgs field to my friends in the pub. You referred more than once in your talk to dark matter. What's your guess as to the probability of whether we'll actually discover dark matter in the future?
So there's a number of different theoretical takes on what dark matter might be. There is a class of theories in which it weighs between, maybe particles weighing between hundreds of thousands times the proton. It could be a large hadron collider. And then you can ask yourself, okay, what is the rate at which such particles would be produced in a large hadron collider, and would you be able to detect them astrophysically? If these particles were flying around the solar system, would you be able to detect them? And I think the answer in both cases is a resounding maybe. And I'm not wishing to get technical, but if the Higgs really does weigh 125 GeV, in many theories that makes things a little bit tougher than maybe what we thought last time. But no, it's certainly something which is entirely possible, but it's not guaranteed.
Who else is, before you speak, has anyone else got a question? Then we can get this microphone moving over. There's no one on the top have a question. You do? Okay. Or you keeping the seat up? Yeah, you do. Okay. Is there any way of getting that microphone up to the chap with the dark jumper on the white shirt? Just so you're represented.
It's on.
And while that's happening, so you carry on.
Yeah, not being very advanced scientist, I'm wondering if the Higgs particle gives other particles mass, and the Higgs particle itself has mass, what particle do we need to give the Higgs particle mass? So?
The answer is the Higgs.
Oh, another Higgs.
No, it's the same Higgs.
Oh, thank you.
So mass generically comes from connecting to this Higgs field. The Higgs particle itself is intrinsically connected to that field. Probably Peter can explain it somewhat better. I hope that's enough.
No. It'll do. No more particles. I can't invent one.
The chap up on the top.
All of the massive particles have mass all the time that they exist, but this boson is very short-lived, so how is it conveying mass to things all the time when it destroys itself?
Okay, well, to be strictly accurate, and I probably wasn't strictly accurate, although I tried to be, it's this universal field that gives the mass. It's wading through the snow, it slows you down. Now, then there is a quantum on this field which you can cite, maybe. You kick the snow, you can think of the Large Hadron Collider as kicking that snow. Snowflakes come up. It's not really that quantum by itself that gives a mass. It's this universal field of stuff.
Can I ask you to, up there, can I ask you to pass the microphone the other way, actually, to the chap here? While that's happening, can I ask you a quick question, John, which is when you get down to these smaller and smaller scales, I struggle to understand even what a particle is. When you get down to quarks, when you get below that, are we talking, is it a lump of energy that is stable, or can you just, sorry, I'm abusing my position, but can you clarify that? Or Peter?
So, indeed, to be called a particle, it has to be reasonably stable. Right? One could give a more precise specification of that. Even Peter Higgs' particle, which is actually pretty damn unstable, never, by any sensible standards, nevertheless lives long enough for us to call it a real particle. This is not so true if I go back here. It's actually one of the reasons why it's so difficult to figure out what's going on the right-hand side of that picture, because then the particle is so short-lived that it's even not clear whether it's really a particle. And there's been a lot of discussion about whether it really makes sense to talk more about particles when you're off the right-hand side of that picture.
Sorry about that. Anyway, back to you lot. The chap, I hope you have the microphone by now.
I'd like to know whether understanding the origin of mass will help us to understand what causes or creates gravity.
Okay. Now, gravity is often said to act on mass. After Newton told us that weight is proportional to mass. There's a coefficient coming in there, which is the gravitational field. Actually, gravity is not given by mass, it's actually given by energy. And an example of that is the famous bending of light. Light particles don't have any mass, they only have energy. But nevertheless, they are bent by the gravitational field. So if you actually look at the correct formulations, gravity acts on energy. Now mass is of course related to energy. If you have a massive particle and you slow it down so its speed is negligible, then the energy becomes E equals mc squared. And for most practical purposes, planets, atoms, they have a negligible velocity and their energy is separated by their mass, and that's why in Newton's theory is mass. But I think that little physics lesson explains why gravity is something really different from mass.
And I think, unless there are any other burning questions, that's probably going to wrap up tonight. And I think Rick is going to... one more burning if we can.
Hi. Well, I'm a biologist, so my question might sound a bit weird, but talking about the Higgs field... So talking about the Higgs field, did the Higgs field suddenly arrive after the Big Bang? Did it just suddenly emerge? And what would have happened if the Higgs field hadn't been there at all? And why did it emerge at all?
So what would be suggested by the Higgs field is that if you go back to the very early history of the universe, there would have been no Higgs snow field. There would have been the quanta flying around, but there would not have been the Higgs snow field. And if you come back to my analogy, one way of thinking about it is that in the very early universe, it was very hot. The snow field would be melting. The snow would not settle, is a kind of describing. Very early universe, it was too hot for the Higgs snow field to settle. When the universe got to be about a picosecond old, we think, that's when the snow started to settle. So before then, particles would not have had mass, at least not in the sense in which I've been describing.
There you go. Thank you all for your questions. I think Rick's now just going to wrap up quickly. And thanks again to John.
Well, John said earlier what a challenge it was to speak after Peter Higgs. My immediate challenge is to speak not just after Peter Higgs, but also Ian Sample and John Ellis as well. But of course, all I have to do is to thank them all on your behalf. But what a lot we have to be thankful for this evening. It seems to me that this has been a remarkable demonstration of what universities are meant to do, to talk about basic knowledge, to talk about the practical implications of basic knowledge, and then to communicate to people within universities, but also to a broader public. I think all of us here tonight, and all of us in the Lucas Lecture Theatre down below, owe all three of our speakers tremendous thanks. It's been such a good evening that I think not just Meryl Streep, but even Margaret Thatcher would have enjoyed it.